Since we cannot pinpoint an exact location as the birthplace of the first star, such a birthplace must potentially be anywhere in the universe. And so is the fuel that produces the stars. The observation of abundant existence of hydrogen everywhere in space gives a good support to this view. Had we ever carried a powerful spotlight to go back to the old days of a no star, and if our eyes had unlimited discernibility, we must see hydrogen clouds spread all over. These hydrogen clouds, big or small, must have started their gathering from some state of very thin density. But how thin? Today's observations suggest that if all materials in the universe are made evenly spreading out, an overall density equivalent to 2 or 3 hydrogen molecules per cubic meter is a good answer. A majority of contemporary scientists consider that a density of 5 molecules per cubic meter or more will stop the universe from expanding and cause a big crunch to the universe. But will Big Crunch happen? In the argument shown by this video, we employ a figure of 16 hydrogen molecules per cubic meter, but it will show that Big Crunch will never happen. Let's first introduce one situation that is well known in Newtonian physics. Assuming a small ball called A is placed inside a hollow sphere, whose wall is homogeneous all over on both thickness and material density. Both ball A and the sphere are located so far away from anything else that nothing can exert on them any gravitational influence. In this setup, ball A and the sphere always have zero gravitational influence between each other. Ball A permanently stays at wherever it has been put, regardless of how the thickness of the wall varies or how its material changes. However, if another ball called C also appears inside the sphere, A and C would move toward each other because of the mutual gravitational force between them. Once A and C stick together, they would not move any further unless another object suddenly appears. With a setup so described, we can increase the wall thickness of the sphere to infinity and replace this wall with hydrogen molecules that have large distance from each other. The combination of A and C would not have moved a bit in this new setup if every molecule could have been somehow solidly anchored at where they are. The problem is that such anchoring cannot happen. All molecules must move if any kind of force, no matter how tiny, is exerted on them. So, the extremely feeble gravitational force from the combination of A and C is able to move them, incessantly luring the free hydrogen molecules to join them from the neighboring space. The material growth of A and C thus resulted further escalates the gravitational force to attract more molecules from even further distance. Material distribution in the infinite universe cannot be absolutely homogeneous all over. Local defect of such distribution must happen here and there. At where a pocket of emptiness occurs, or at where local material concentration is higher, the aforementioned gravitational recruiting must happen. The ferocity of gravitational cannibalism between all sizes of gathering can only escalate its magnitude as time progresses. Besides material growth, the temperature of each material gathering also gradually increases, because materials crashing at it from a distance must release their potential energy, which must convert into heat. The accumulation of heat is multiplying in magnitude as time progresses, because the mass quantity of the materials from farther and farther distance is incessantly escalated, and the farther and farther distance can only mean higher and higher potential energy. Finally, somewhere in the universe, a catastrophic event happens. An unusually large gravity body is formed at a location where all neighboring bodies also happen to be big. Of course, the word neighboring may easily mean distance of light years. By some coincidental chance, all the neighboring bodies just happen to clash at this unusually large gravity body within an extremely short time duration. The heat thus converted through this violent clash cannot have enough time to escape, but pushes the temperature of the hydrogen gathering to the degree that the critical temperature enabling a nuclear fusion is reached. A fierce explosion immediately launches, ejecting countless burning torches to the neighboring space in all directions. Only after this first explosion did the universe begin to have light, irreversibly converting part of the universe into a visible world. With the introduction of such light, our story has just begun. The visible world is incessantly expanding, at the expanse of the generous yielding of the invisible but infinite portion of the universe. It is this expanding visible portion that has been puzzling the Big Bang believers with an illusion that we have an expanding universe. From a state that's 16 molecules per cubic meter more evenly spread all over in the universe, to a state that a fusion reaction can be ignited, a good 9 billion years would have lapsed according to calculation. If we ever give credit to the age of 13.8 billion years claimed by the Big Bang theory for the universe, at least another 9 billion years must now be added to it, making the universe age at least 22.8 billion years. However, at some point, tracing back to an even older history of the universe would have lost any meaning for us. There is nothing wrong for us to believe that the universe is eternal. This 22.8 billion year age should give us confidence about the universe's eternity.